Bernoulli's principle. Let us consider a fluid flowing in a tube, then the work is done by the external forces at the ends of the tube by forces F1 and F2. Let F1 does a positive force in the direction of the motion of the fluid and F2 does a negative force opposite to the direction of the motion of the fluid. Now, in order to understand the Bernoulli's theorem, what I'm going to do, I'm going to consider a diagram. So here is my diagram where you can see P is a point H1 over the Earth's surface where the area of cross section at this end is A1 and let mass M1 is entering the tube with a velocity V1 at point P. In the same way, let point Q is at a height h2 over the Earth's surface and let the area of cross section at this end is A2 where mass M2 leaves the tube with a velocity v2 in time t. Now, let a force F1 acts in this direction and force F2 acts in this direction. Because F1 does a positive force and F2 is basically a negative force, and these two forces are acting at the end of the tube due to the motion of the fluid. Then the net work done by these forces on the system is given as W net is equal to F1 x1 minus F2 x2, where F1 and F2 are these forces right here and x1 and x2 are the distances traveled by the fluid. If we simplify further, we can write force as pressure times area. So we have P1A1 x1 minus P2A2 x2, where P1 and P2 are the pressure at both the two ends respectively. If we simplify further, we will write distance as velocity times time. So x1 will be v1 times t and x2 will be v2 times t. So if we simplify further, we will write W net is equal to P1 A1 V1 t minus P2 A2 V2 t. And we know that from the equation of continuity, A1 V1 is equal to A2 V2. So basically I can substitute this A2 V2 by A1 V1. And if I do that, I will write W net is equal to P1 A1 V1 t minus P2 A1 V1 t. As you can see, A1 V1 t is common. So we will write W net is equal to A1 V1 inside the bracket P1 minus P2 times t. So we have work done W as equals to A1 V1 t times P1 minus P2, and let this is our equation number 1. From the equation of continuity derivation, we have M1 is equal to rho V1, where rho is the density and V1 is the volume, and if we simplify, we have rho A1 x1 and that is equal to rho A1 V1 t. And in the same way, we have M2 is equal to rho V2, that is equal to rho A2 x2 and that is also equal to rho A2 V2 t. And these two derivations are from the equation of continuity, where A1 and A2 are the area of cross section at both the two ends respectively, and V1 and V2 is the velocity at which the fluid is entering and leaving the tube respectively. And we know that the same amount of mass of the fluid will enter and leave, so we can definitely write M1 is equal to M2 and that is equal to M. And if we simplify, we can write M is equal to this term and M is also equal to this term, because M1 and M2 are equal because the same amount of liquid is entering as well as leaving. So we have M is equal to rho A1 V1 t and that is equal to rho A2 V2 t. If we simplify further, we can definitely write M over rho is equal to A1 V1 t and that is equal to A2 V2 t. Now let's substitute the value of A1 V1 t over here with M rho, because A1 V1 t is equal to A2 V2 t and that is equal to M over rho. So if we substitute in equation number 1, we will write W net is equal to M over rho P1 minus P2. and let this is equation number 2. Now the net work done on the system by the external force is given as W net is equal to change in potential energy plus change in kinetic energy, and let this is equation number 3. Now we know that since the fluid is moving with velocities v1 and v2, then the change in kinetic energy is given as delta k is equal to 1 over 2 m v2 square minus v1 square, and let this is equation number 4. In the same way, we can find the gravitational potential energy, which is delta U is equal to mg h2 minus h1, because one end is at height h2 and the other end is at height h1, and let this is equation number 5. Now let's substitute equation number 2, 4 and 5 in equation number 3. So we have this expression, and the reason why, because net work done is equal to change in kinetic energy plus change in potential energy. So we will write m over rho p1 minus p2 is equal to 1 over 2 m v2 square minus v1 square plus mg h2 minus h1. Let's simplify further. So what we will do, we will cancel m from both sides, and then we will multiply this rho to the other side, and if we do that, we will get p1 minus p2 is equal to 1 over 2 rho v2 square minus v1 square plus rho g h2 minus h1. What we need to do, we need to consider all the terms with 1 on one side and all the terms with 2 on the other side. So let's rearrange, and if we do that, we will write p1 plus 1 over 2 rho v1 square plus rho gh1 is equal to p2 plus 1 over 2 rho v2 square plus rho gh2, which simply means that this term is constant or the same for all the points on the tube. So if we write the generalized form of the equation, we will write p plus 1 over 2 rho v square plus rho gh is equal to constant, and this is basically known as Bernoulli's principle, which simply means that if you add these three terms at any point on the tube where the fluid is flowing, then that term will be, or I should say, some of these three terms should be equal to each other for different points. And this is how we define the Bernoulli's principle.